Today we're gonna have two larger topics, and I'm not sure if I'm gonna be able to cram both into one session. At least not while giving them both the proper amount of time and breadth they need, so to speak. And the first one we're gonna look at is a specific concept that you've already seen and used a couple of times. You might not have been aware of it, but it exists. And it's used for a couple of very interesting things. And the way it's used is often a bit more complex than what you've been using it like. To start with, as usual, some example code. Let's see. Let's start with this. We're gonna make a class the game, and the game will have, let's create the other class first. We'll need some settings again. I got settings. Let's just put in some dummy like FPS again. Doesn't matter. Settings, and we're gonna need a controller. Public, let's first make just a simple class controller. Doesn't really matter what we have in here, like public, let's say int get input key. And for now it's just gonna return 0. We don't really care about that. The compiler does though. And what else? Let's say public class engine. Let's say physics engine. Something more specific. Let's not care about the implementation. And the game will have public settings. Let's just make them all read-only properties. We have a controller, and we're gonna have a physics engine. And we're gonna have to add a constructor to fit all that, like this, so. And now I can, in our main method, just create a new game, which needs new settings first. So we would have to create settings, and we have to create controller and a physics engine, and then we can pass all of those into the constructor, and we have our finished game. Well, instance at least. And in the last sessions, well, specifically in the last one, we didn't use controller directly. We noticed that there are different types of controllers, and managing them all is easier if we don't expect game to understand them, and just have some commonality between all controllers that game is seeing, and the specific implementation doesn't matter. And we did that with an abstract base class, but there's a different way we can handle that with an interface, which is not all that dissimilar from an abstract base class. So we'd say this controller is just a controller. What am I missing? Interface, that's better. And we're gonna say the input key is a method of the interface. And what the game actually cares about is just the interface. All right, so real controller implementation real controller implementation implements iController, and iController is all game cares about. And this way we can, in the background, just switch the actual controller out and implement some other type of controller later on. And last time we used a couple of different factories to create different types of controllers depending on settings and the current context. And game will just work in all of those cases, which is really good. And this idea of I'm just telling game you get a controller, but not which specific controller. I'm just giving you the information it's gonna be a controller, and all you know about controller is that they're gonna have a method called keyInput. Key. Which, okay, the name is a bit confusing. Doesn't matter. We can consider this dependency injection already. I mean, this is all we need. The game expects an interface, and we can provide actual implementations of that we give the game when we compile down here, or, well, more specifically during runtime, we pass on an instance of an iController, whatever type of controller you want. That's something you've done probably a couple of times already. And you've seen already the advantages of this system. Just in general, the advantages of having something more abstract in here. Not a specific implementation, but something more abstract, like an abstract base class. Or just a parent class doesn't need to be abstract. Or just straight up an interface, which is as much freedom as you can give this, aside from just passing on a delegate directly. But delegate would be just a simple method, so interface is the next best thing, which can have multiple methods in there. And that gives you as much freedom as you can. And later on, when you use this class game, you can inject any kind of class in here, any instance you have that fulfills the conditions for iController. And this practice can be made a bit more loose by having a framework that's specifically designed to work with dependency injection. Now, personally, I've only encountered that system when I was working with ASP.NET, but the standard libraries have classes that deal with that handle that kind of thing, and there are a lot of larger frameworks, not just for web, that have special features in the library that help you with managing different instances and creating objects that expect certain types of instance without being too specific. And all you actually need to know for dependency injection is you use an interface or something more abstract that can be different actual, I was tempted to say physical, actual implementations of something. And that leaves you the freedom to pass on different types of stuff. So basic abstraction, you can also already consider this very simple dependency injection. This is all you need in the game class. But something cool you can do if you do work on a large project that is expected to do a lot of different things, like create a lot of different instances for very different things, very different objects that have also dependencies among each other. So game needs all of these different instances, objects, and then you have to manage creating actual implementations for all these different types and instantiating them during runtime and then passing them onto the game so it can use all of that. Let's make a new class to demonstrate this concept. Let's call it for now just cache. No, let's not cache. Cache sounds wrong. Let's call it source. And conspicuous name. Conspicuous? Conspicuous? inconspicuous. Whatever. And this source class is something we're gonna instantiate once at the start of our program. And we're gonna use this class to manage all of these instances and match them together. Let's maybe expand this a bit. Let's say the physics also need settings. No, let's not do primary constructor. Let's do... That's better. And we're gonna do like that. Ah, refactoring tools are so useful. All right. So we have 3 different classes or types now that have their own rules for creating them, and they have some dependencies on one another. So the controller is standalone, doesn't need anything. Settings doesn't need anything. The physics engine does need a settings instance to work, to create, and the game needs settings, a physics engine, and a controller. So these do have dependencies among one another. Game depends on physics engine and settings. Physics engine depends on settings. Settings and controller don't have any dependencies themselves. And our source class is going to help us with managing all of these dependencies. And this is where the quote-unquote real dependency injection kind of starts doing its magic. Basically, whenever I hear dependency injection, I only see it in the context of there's a framework that has special libraries to deal with that. And what we're gonna do is we're gonna add a method called add, which will add an instance, and we're gonna have a method get, which will get us an instance. Now, which instance doesn't really matter, it can be anything. So to deal with that internally, we're just gonna package them all as an object for now. Let's keep things simple. And actually we can make our life a bit easier right now by just going for an internal private read-only dictionary. Let's keep that empty for now. Keep the dictionary. This one we call cache. And in the constructor, we just start the cache. No, not those. Good guess though. And this is what we're going to use in the add and get method. And what we want to store is the type and the very specific instance. So we want to store for each type one instance. We store that just as object because we don't want to be tied down to one type only. So when we add something, we want to add based on its type, and we want to get the instance, and then we can just cache.add. We're going to simplify things. I don't care about concurrency right now or error handling for when there's duplicate keys and whatnot. We're just going to ignore that. This is a very rudimentary, wrong implementation, so you can see what's actually going on. But this is not a correct implementation. This has way too many issues. Just a heads up. So this would add it, and then we do on the other side a get method, which will take the type and return the object. For that, we can just go cache and the type and return. Right? So very primitive setup. We basically have just a simple dictionary that lets us store and receive specific instances based on their type. But that of itself is just the dictionary alone. That's not too useful. Let's add an overload. Let's make this a bit easier to use by making this generic. You can pass on any kind of instance, a generic instance, to the add method. And then we can get with type of the type of the generic type we add. And then we can simply call the other add method using type and instance. Now we get an error because instance might be 0, or not 0, null. Let me just catch that. Instance is null. If that is null, just ignore it. We don't store anything that's null. That doesn't make sense, so we just return, and this is not compilable. And we'll do the same with the get method. Again, we make it generic. So instead of specifying the type, we just have a generic type. And internally, we just get that and then return. Type we get and cast it to T. So what we can do is, for example, for the settings object now, we go source.add settings. And then I can also go source.get settings. So I just call the add method on source and just pass it my instance, and it will internally figure out what is the actual type of this and what do I do with it. And when I want to get a specific instance of a type, I can just put the class name in here as a generic argument. Or if I have the type, of course, I can still go like this or this, though that doesn't make too much sense. And I would have to cast it myself if I use the pure object version. But I can use that. It might be useful for some cases, so we leave the methods in there. But I can store stuff and I can get it back. Alright. One advantage of these systems, this is basically a blackboard model. I can now also store the... actually, let's complete this. Instead of storing this in a variable, we'll just pick the constructor in here and directly add it to source. And if I need it down here, I'm gonna have to do source.get settings. I have to do that in there as well. Right, and then we can do the same with this control implementation. We're gonna do source.add. Just add it to our source. It doesn't have a specific name, and when we need it, .get and recontrol implementation. That's how we can get it back. Can do the same with physics engine. Can... Yep, that's the wrong one. I didn't need to do that. I can also go just arc and then source.add. Add the physics engine and get the physics engine back out in here. Right. And if I pass on this source object throughout my code, maybe make that even a static variable or something, but somehow just pass this one source object, I can also share all these other instances. Which might be interesting if you're not sure what kind of objects you're gonna need later on. Maybe we're gonna extend game with some more variables it needs. And instead of adjusting all your code to make sure you store the variable for that additional type anywhere and pass around, you just add it to source and game can figure it out. I mean, in theory, you could just pass in source and inside the game constructor, you have all the get methods. That's a possibility, but that's not what we're gonna do. There's a way more interesting version. However, there's more to this that bothers me. Before we start with the cool stuff. Right now, I have to specifically ask for the real control implementation. Because when we store this, we store specifically the type real control implementation. That's what we do in the dictionary. And the only way to get that back is by actually using that type, real control implementation. But maybe I just want an iController, because that's what game is asking for. If I try this, then the type of in the get will be the type for iController, the interface. And we haven't stored anything for the interface, we have stored for the actual class implementation. But these are two different types. Even though this object we stored is also an iController, that's not the key for it. So we need to change this method to also allow the interface. So we could do something like cache.tryGetValue out object, let's do it like this, direct match. If return direct match, and yeah, cool. Forgot the nullable, like that. But if we didn't find that specifically, and type is an interface, then we could instead just go through cache in its entirety. We'll just look at every value in there. We don't really care about the key, but we do care about the value. Let's call it instance, not isnance. We call it instance. That's better. And we're gonna check now if the type is assignable from instance. Okay, you should get the type first. Instance.getType. Actually, why bother? I'm dumb. I'm dumb. We already have the type. This is already the direct type. That's what we do. Instance type. Type. Like that. We don't really need the interface in this case. Could also be abstract classes. Let's keep this open. That's already good enough like this. And otherwise, let's make throw new exception, no match found. Just so the compiler's happy that we don't have any returns for the other cases. So assignables from, we check if instance type, so the actual instance could be stored in a variable with this type. So if type is a base class, a parent class of instance type, that will work. If type is an interface that the specific instance implements, that will all work. If not, then not. And so with this, we should be able to do iController. Let's test the real controller first. I never tested if my code actually does the right thing. We should be able to get to game. Yep, nothing broke, and we have a fully functional game. And let's look at game. We have a controller, we have physics engine, we have settings. That all worked. And if I switch to iController, because of our changes, that should also work. I can actually go into the code down here. So let's look at the call stack. Looking for the settings. Settings. Now we're looking for iController. Type right now is iController. That's what we're looking for. And there was no direct match in the cache because we stored in the cache only recontroller as a type. So we can go through all the types in here and eventually find one that is assignable, like this recontroller, which we can return. And well, okay, last one, our game is done. game is now finished, again with the recontrol implementation, even though for the source we only demanded to have an iController. We didn't care about the specifics. Now for something like the physics engine, we created a new type that we wanted to add to the source, but to create it we also already needed data from the source. So let's be a bit clever about this. Let's offer an option to add methods instead of just direct values. Sorry, I wasn't quite sure how to phrase that. Let's abstract this slightly. We're gonna make some inner private classes now here. Well, let's actually make a private struct. Private struct, and that's is called instance container. Instance container. Not instance. Instance container, like that. And let's make this read-only. Public read-only type. Yeah, that works. Like so. And we're gonna make a second container. Instance container. Func container. This one is gonna store a type and a function. Basically a delegate. Pass on a method that can be called later on. Creation method. And this creation method will receive a source to read data from, and it will return something. Return the instance that we wanted to create. Source, object, like that. And we should also rename the constructor, of course. And now to put them both into one single data structure, we're gonna add an interface. Interface container. And container is gonna have method object, get object, both get source, even though one is not going to use them. Container. And we add the method. And this is just going to return instance. Doesn't need the source. And this one is going to call creation method, which does need the source. And instead of a dictionary, we're now just going to store a list of my container. So, and when we add something, we're going to add new instance container, type instance, like that. And of course we have to change this. We can't look up the type directly anymore, but can do it container. Oh right, I should add object type. Should add that as well. No, not get type. Get type is already another method that exists. Oh, get instance type. Yeah, okay, now it's complaining. Good. Return type. Actually, let's make this like so. And copy that over. Switch container dot get instance type, return container dot get type. Get object. That's better. This. Right. So we have two containers internally, one for functions, the other for instances directly, and we can both put them into one list because they share the same interface. Now when we add something, we can do that in two different ways. We can do it either this way, or we can do it with a function. Function that receives a source and returns an object. We create a new func container. And the add method for that will, of course, also be slightly different. We don't have to check that anymore. And that should work. Actually, let's rename them. Add instance, and we rename this one down here at func. Yeah, now it's complaining. It's complaining because that's a T and not an object anymore. Do I just cast it? We can just create a new function here. As instance as not the nice way. This should do the trick. It's not doing the trick. Why? What am I doing wrong? I'm doing something wrong here. Right. Grab. Yeah, no, those can stay. Let's remove those. Why? I'm blind. I know I'm blind. I just don't understand why. Instance is not null. This is not so null. Why should this be null? It's not null though. Okay, I'm slightly confused by the nullability since I'm... Oh, wait, because T is possibly a struct. That might be an issue. And sometimes it's not, and it's... Yeah, there's no nullability analysis because it's not clear what T is, currently. Alright, so that's not as quick and elegant as I wanted it to, but it still works. So what we can do, instead of doing this line in here, we can do this instead. Fuck, like that. And this does actually make quite a difference. So before, in this line, I created a new engine directly, and this finished instance of the engine was then passed on to our source object to be stored and referenced later on, like here. But now I'm just storing a method that allows us to create the instance later on. So when I call this source get physics engine, it will look up the function that we defined down here and then actually call this method and have the constructor called. So this physics engine isn't created until we actually hit this method down here and request it for the first time. Until then, there is no instance of physics engine. That also means that when we add this function, we don't actually need the finished settings yet. So I can just go up here, define this function, and everything will work. The old code had an issue because physics engine requires a settings object. Up here, there was no settings object yet. So the constructor would fail. Let's actually try that. So the old one, add instance. So let's look at settings. Let's comment this one out. Now we run it. We get an exception. Try to run this code, this line. Let's specifically step over the line. Bam, exception. Because there is no settings it can use to create the physics object. Now let's switch this up. Let's put the old method out and put the new one in that uses the function. No problem. Because we only defined the function to create a physics engine. But we didn't actually create it yet. Can now add the instance for settings and a controller. And now when we create the game, there is a physics engine, because now it can actually call the method and safely call the method because a settings object exists. So we can just put instances in there directly. That's fine. And that can be useful in and of itself, because it helps us manage all different types of instances without having some centralized location where we store references to all of them by name, like a central static class that has all the different variables we need. We put them all into one large container that can store everything. But by allowing us to add functions that only detail how to create the instance but don't create them directly, we can delay the instantiation of these objects to some time later in our code, when they are actually needed. Beforehand, I needed to make sure the order is correct. I had dependencies. Physics engine depends on settings. So I had to make sure that my physics engine was only created, this constructor was only called after settings. So in my old version, I needed to write this line after I have already had this line. Didn't work any other way. By allowing methods in there, I can change the order in which they are created. I can make them independent from the order in which I add things. So the order in which I add stuff to the source has no influence over the order in which it is read from the source. So I can just put them in any order I want. And if I want to be really fancy, I can actually split this into two parts. One part, one phase basically, where I just add stuff to this source object, either directly or through methods that detail how to do that. And then a second phase in which I actually go through this list and instantiate all the stuff I need. So everything that had a method in here, I could instantiate it now. Or I could just leave it out entirely and leave this step and only create new instances when I actually need them. That's another advantage. By only defining the method how to create it, I'm not actually requiring the computer to build this object in its entirety, which might take precious resources. So I can just add it in the beginning of my code. I can add the definition for, okay, if I ever need the physics engine, this is how you would create it. It's all there. But if I never make this get physics engine call, I'm never gonna call this code, and I'm never gonna bother with creating the object and wasting all those resources. If I do ever need it, it's just a one-liner to add it, and suddenly I do request those resources, but I create a finished working physics engine. So I have way more flexibility in programming. I don't have to worry about, do I actually instantiate it now or maybe later? When do I do that? Do I actually do that at all? And don't have to worry about that. If I never use this, no resources wasted. I mean, except for this one delegate and the container, but that doesn't really count. That's not much. This one call over, that changes everything. Now I am instantiating this. And then when I don't need it anymore, I can drop it and I'm not wasting the resources anymore. The code exists, I did my work, and any other person in my team could just make this call and they get a physics engine. They don't have to worry about how do I create it. Very useful stuff. And it gets even cooler. See, right now I still need to define exactly either how to create my physics engine, or I have to actually make the call myself to create the physics engine, or the game in this case. We can let the system figure this out itself. So right now, what I would do with this, for example, I would wrap this up again in a source.function, and then source, but through a function everywhere, so we don't actually need to instantiate it. And then I can do source.get game. So, and again, I can just put that up here, doesn't matter. I can have the code that creates my engine in the very top. And only then do I actually add the other methods or actual instances I need to create the game. Doesn't matter anymore, the order. As long as I have everything in place when I call this source.game, it will work. Just to be sure, it still works. No errors, no compilation problems, no exceptions during runtime, it worked. Actually, let's make a breakpoint and see for ourselves. We do have a game with everything in there. Cool. Let's talk about this last case here. We didn't find a match. Well, that we didn't find a match doesn't mean we can't return anything. Because if we don't have a match, we just create one. And we're gonna do the very, very simple method. We're gonna first look at type.getConstructors, and I'm gonna just look for public constructors for now. And this is again very, very stupid system. I'm just gonna look for the very first constructor. Doesn't have one, we're just gonna break, and then constructor info.parameters, get parameters dot. Let's store them in the variable parameter infos, and now we have the info. What is the constructor for this type? This type, we don't have it yet. This would be the case when I call addGame down here. I call getGame without providing a game instance directly and without this method that tells the system how to create it. So we would end up down here, where we request the different constructors that exist for the class game. And we just pick the first one now. That's not the best strategy, but it's one strategy. And then we're gonna look at the parameters for the constructor. And now, yeah, actually that's correct, autocomplete. Each parameter. Now let's do it with a for loop and with a normal one. I equals 0, I less than parameter info store length plus plus I, and we're gonna do parameters I equals, and now things get interesting. We make the get method, we basically make it recursive. Parameter infos I dot parameter type. Can you guess where this is going? We look at the first constructor in our method, in our type. Parameters of first constructor. And now for each parameter in this very first constructor we find, we're gonna call this get method, which will try to look up that type in our source itself. So what would that be? Well, the very first constructor is the only constructor we have right now, which is this one. And these are the different parameters, and these are the parameter types. So what we're gonna do is we look up a value for settings, and oh wait, didn't we add something to the source that is a setting? Same with controller, we do have a controller down here, and we have a physics engine, which is the last one. So every single one of those calls here will look for something else other than game. It will look for a specific type that is requested by the constructor of the game, and will look for an instance of that. And so these parameters will be actual instances we would get with these calls, these get calls. This is what we're doing right now, just automated in a loop. We do all of these 3 get calls and store the results in one object array. And now we can do invoke of this constructor info with our parameters. We're just gonna leave the other values aside and return. So I could add this function, but I'm leaving that commented out. And I still get my game. So this isn't needed anymore. Actually, this goes further. Oh, just reset it. But yeah. This physics engine is also a very simple type that only needs a settings object that we already add in here. No problem, we drop it. And when we call the game, it will still be there. The physics engine will exist, and it will have the settings stored inside. And the game will be fully featured. This is the end result of our framework. We can use it to store instances we create in one part of our code, usually at the very beginning. And those are instances that require some specific knowledge from the programmer. You have to define them at some point. For example, the settings might be loaded from a file somewhere, and you have special logic to read that settings file. And for the controller, you might need to decide which type of controller based on different conditions. So maybe you have a factory, like last time, and you store that instance. Or maybe you have special types that require some complicated setup, using large builds maybe, build patterns, and you store those, maybe not directly, but through a function that then later can iterate through the existing data and create something. But all the other types that don't need anything to be created, or types that only use values that you can just use already, that you have already, those can just be requested directly. And the logic will call the normal default constructors and add it for you. So with this game, the constructor, as you can see, is not called at any point in time. 0 references, it's never called directly. But our source will call it and create it. You can also do something else, like a public class, empty class, default constructor, empty, that would work just fine. Public int default. Oh, let's do it. Default equals 5. So empty constructor. I can just go ahead and say source.get, and I want empty. It will call the default constructor and fill out the values, and we get a proper instance of empty because we already had everything we needed. If we actually needed to have an integer here, integer I, and then that, let's call it default. Nah, let's not call it default. This would not work anymore now, because empty doesn't have a proper constructor we can use anymore. So this one would be one where we either have to provide directly the instance, or we can do it through a method. For example, at func, maybe this is based on the settings. So let's start get settings, and then dot FPS divided by 10, like so, and that's what we're going to put into the constructor call like that. So if we can create it directly, we can still add a method that tells the system how to create it instead of creating it directly ourselves. And successfully created an empty object with 6, which is 16 divided by 10. Now I call this source, but usually you would find something like service provider as a name. But I called instances that are stored. These are actually services. At least in ASP.NET that would be called that way, and I think the default library calls it service. There's a special interface, service provider, with a getServeth method that looks very similar to our get method here, right? So this would be actually get service type. And iService provider is part of the standard library, and there are some actual service providers. There are a lot of test service providers, which is another thing you can do quite easily. If you route everything through a source instead of storing directly in a variable, it's quite easy to change data later on. Like you can imagine, instead of just adding stuff, you might also add some method that could replace stuff. Or you have special rules for overwriting stuff. If I add another instance of settings, it will overwrite the old one, for example. And that way you could add special classes, like last time we had different types of controllers for testing purposes. So maybe my default code would add a real controller, but my test code would then replace this instance in our source object with a debug controller. And the main code would still simply use the source object, our service provider. Let's actually rename this to just get an instance of controller, which just happens to be now a debug controller instead of the real one, without really changing anything in the code. Very convenient. Downside to these types of systems, these frameworks, debugging gets tricky. At least I find it very confusing sometimes, because there is no direct link from this constructor to this code up here. If I later test my code and I find that this game has somehow weird values, like maybe the controller is a different one, or maybe the physics engine is a broken one, like a test physics engine or a prototype I actually dropped out, I don't use anymore, and yet my game seems to use it. Well, since I didn't create the game myself, I can't really go back the trail to figure out where this physics engine came from. The only way I can tell is by going through the different calls to service provider which add the physics engine. And even then I'm kind of out of luck right now because I never added a real physics engine. It's all out of thin air, so I have no idea where this physics engine came from. This physics engine itself was just created directly, but also again without being called anywhere. So the internal logic just created a physics engine which was used in here, and that happens to be a wrong one. And now I have to figure all of that out. So the usual tools for debugging are gone. You specifically throw them out the window in favor of some advantages you have in other parts of your code, by just simplifying things. Or, well, actually it's mostly simplifying, because now a very large project with hundreds of different services, hundreds of different instances of different classes that are needed across your entire project, they are much easier to handle now and organize and extend. Very convenient. Comes at the drawback of difficult debugging. At least that's my opinion. But that's everything today for dependency injection. Let's talk about something else. Something else that might actually be combined with dependency injection, that becomes easier if you use dependency injection, at least the very basic idea of it. Plugins. Imagine I publish a game and I want explicit mod support. I want people to be able to mod my game. And the easiest way to do that is by offering an API that people can use. I allow them to create plugins, systems that they can create and write on their own, and they just add those libraries, add that code to my existing game, and my game will just load that code and use its content. My plugins have a few tricky parts to them. Let's just minimize everything here because we won't need that for now. Board all. For my code to use something, let's say I want to have a class of runner. So this is my main class that does something, that's doing something by default in my program. Public void run. Okay, very simple thing. So runner, create a new runner and runner.run. Call it. Running. Console.read. Okay. So calling the code, we're running. Cool. And now I want people to write code that replaces this functionality. I want them to be able to override this default behavior. Or maybe add behavior in the first place where nothing happened before. That has two major issues. The first one, maybe the bigger one in UIs, how do I load this external code? If it's not code that exists when I compile my program, how can I use it? Well, let's make a simple example. Reloading this other project I have here. So far it's empty. There's nothing in here. This is our current project that we are working in. And this is just a library with no content so far. And what we're gonna do is we're gonna add a new class in here. Let's, for now, just make the same we had already, a runner class. Let's make it public. Public class runner. Public void run. The console output plugin is running. So let's compile this. And if we look at the output down here, this is where the compiler stored the file. And the simplest thing we can do is during runtime, we can load a file from here. So we just ignore that for a moment. This DLL is an assembly file. Actually, there could be many assemblies combined into one DLL, but for now it's one big assembly in one single library file. So I can just go for assembly.loadFile and give it the path to our file on here. And the return value is an assembly. Loaded assembly. And we can do that at runtime. During runtime, while your code is running, you can just load assembly files. That is not an issue, because the entire framework actually does this all the time. Not all your code is loaded the moment you start your program. It's only loaded when you actually need it. C# is a bit, or .NET in general, is a bit lazy, which has its advantages. If you don't use a specific part of your code, you don't load those assembly files, which would take processing to properly read and evaluate, and it's also taking away some memory. If you don't need it, why load it? So we can, at any point, just load an assembly file, and then we can check this assembly file to see if we find anything interesting in there. We can get exported types. Those are just the different types that we defined in that assembly. So right now, that's only this runner class. So we can just go for exported type 0. There's only one class, we know that for sure. We're going to look at that. I know right now, because that's how I programmed it, this will be the runner class, and then I could now go to get methods and try to read that method info and then execute it. That is possible. Using reflection, we could go through the entire process and call everything. Just to demonstrate, runner type is indeed who needs who dot runner, and declared method. Yeah, okay, it doesn't let us know, but declared methods. We have the run method. We could call that. It exists. This is not very convenient. We can make this easier on ourselves by adding a dependency from our main program to this other program. Let's try that. I'm adding a project reference. So now we can see we have a project reference to this other file. We already talked about project references before. So instead of loading the assembly ourselves manually, this code that will work itself out has knowledge about this other assembly already, and we can do su.runner.var run.run. This calls the library, no problem. Plugin is running. Cool, that works. Only we have an issue now. This is my main program. This would be my game, basically. And this library that we now added the dependency on is some code someone else wrote later on. This didn't exist while I created my game. We added the dependency as if it already existed, but it doesn't exist technically. I'm adding a dependency on something that doesn't exist. We can't do that. We cannot add a dependency in here. Our game cannot depend on the plugin. So there's a little trick we do. Instead of depending on this external library to call the data directly, we instead have, for example, an interface, iRunner, which will have a run method. And now we add a dependency in this external library to our main program, which is something we could do later on. If you create a plugin for my game, it means my game already exists. The libraries for that probably also exist. And you can create this library with a dependency on the actual main program. That direction works. And now from this other file, this other library, we can actually reference the iRunner interface. iRunner is defined in our main program, which the external library has access to. The main program still doesn't know what the plugin code is. It doesn't know the assembly, so we're gonna have to load this in again. But now that we know that it will implement the interface, or at least we can give that out as a requirement, we can test if runner type is and has implementation. Runner type dot get interface. Right, is that an implements? Okay, get interfaces. Interfaces dot any t type of iRunner. Actually, yeah, okay, let's do that. That will work. So what we do here is we go through all the interfaces of this type we found, and we're going to compare that to the type of our interface iRunner. And those need to be the same. Let's check any. It was false right now. Didn't find any. Interesting. Let's go back to our runner. Let's compile this once more. Let's try again. Now any is true. That's something we have to look out for now, because this project depends on our main program. Every time I compile this, we look at the output down here, to up to date. It will also compile, it will work itself out. We added a project dependency in here. So Visual Studio knows when I compile this assembly, it will also reference the code from this other project. So if that's not already compiled, compile it now first and then compile my code. Let's actually try to rebuild the entire program. Look at the output again, rebuild. Look at the build order. It will first compile, it will work itself out. The assembly we have a dependency on. And once that dependency is finished with compiling, then we can start compiling ourselves. But our main program doesn't have any dependencies. So if I build that, it will build only itself, not the other code. So if I make any changes in here, like for example adding the interface, our main program will not see that until we manually go back and compile this first. Only then will the DLL be created for our main program to see. So that's something, if you test your interfaces, your plugins, you have to keep that in mind. Your dummy projects that you test with, you will have to manually compile them unless you modify the MS build process a bit to include the other dependencies, which we could do by doing build dependencies, build order. So I can, okay, I can't do that right now because Visual Studio doesn't let me. There are systems in Visual Studio where you can tell Visual Studio to compile other projects alongside your own project without the projects themselves having dependencies. But now Visual Studio rightfully complains when I do that, that there's a circular dependency because of that, which makes sense. If I compile this first one and tell it first compile this other one will tell compile this one, and then yeah, that will not work. But you could mix and match to at least compile afterwards manually by changing MS Build targets. We might have to talk about MS Build at some point. I'll keep that in mind for future projects. Anyway, we now have this. Now let's change this code up a bit. We have all the exported types in our exported assembly. Now let's just assume that there's a large project in here and there are lots of types. Right? And we're just gonna go for exported type dot get interface. We can just copy this code directly. Let's what's going on? That's better. Type interface type equals type of runner. Type of actually takes some resources, so I'm not going to call that in the loop all the time. Instead, I'm just stating that once and reusing all the time. Not if continue, and otherwise we're gonna store type implementing type like so. Type. Let's start with null, and yes, I forgot to add nullability like so, and then implementing type dot I don't know what I'm doing. I don't know what I'm doing. Export a type. All right. We're just gonna assume that we're definitely gonna find an implementing type. You could add actual code in here to handle that we don't find any matches. But now we have implementing type, and we know this is technically an iRunner. And we're gonna make things simple and assume that we definitely are able to create it. So we're using the activator class, and we're just gonna create an instance for this from implementing type. And it's not gonna be null. And let's also assume this is not gonna be null either. And then all we need to do is cast this to iRunner. Now we don't know the actual type now. I mean, we know the actual type, sure. But our current main code doesn't understand the actual type that we defined in here, because this is a class outside of our main program. We never taught it how to deal with that class. But we did tell it how to deal with iRunner, because that it knows. So we can cast it safely to iRunner, which it matches. We basically bring it down to the least common denominator in a way. We expose this instance we create to our main program using the actual interfaces that we know. We could also do this with the base class. So instead of an interface, we actually have a normal parent class on here that this inherits from, and we use that. Would work just fine. Oh, I had complaints now because of, yeah, okay. Or not. Matter of taste. And now we can call instance.run. Right, let's try that. Plugin is running. All right, so what have we achieved so far? We have two different projects. Our main program, which is just a standalone program that can work entirely by itself and has no dependencies to anything outside. And a separate library that has a dependency on our main program that the main program doesn't know about. Now, during runtime, our main program will look for a DLL file, library file, somewhere on the file system and load that assembly, and we'll then check the assembly for any type that's defined in there that implements the iRunner interface. The iRunner interface is of course an interface in the main program that the library that we load also knows, because it has a dependency on us. So it's like a common language element. The main program doesn't know the external library, but both the external library and our main program understand iRunner. And so we use iRunner as a common language, basically, as the interface between the two. Not the interface, but as an interface, as an API interface, as a, what do you call that? I can't remember the word. Yeah, as a common element. Common ground. Let's use that. So I can call it, and I'm calling the external library. And in theory, I could add another project and load that assembly, and my main program would be able to execute that. But my main program is, of course, meant to run on itself also. So if it doesn't find the assembly, maybe it's just calling a default implementation for itself. So if, let's see, if implementing type, let's be interesting. If implementing type, no, I have an ID. No. Let's do it after all like this. Let's do this. Implementing type is null. Then we're gonna do instance equals new runner. Do we have a runner still? All right. Else instance equals type new runner. Yeah, why not? Okay, not the most elegant. But this way, if our external library doesn't offer this, so let me recompile. We default to our own version of runner. So this is the default implementation that we use. Default runner. And the external one will be plugin runner. Like that. Makes maybe more sense. So default is running if we can't find anything in the plugins. But if we do have a match in the plugin for the iRunner interface, let's compile, of course, not forgetting, compiling. Then the main program will find a match and will use that instead. That's how we can add new code later on. But that's just the first issue, loading the library itself. The second issue is compatibility. And this is a bit more complicated and potentially not needed. It entirely depends on what you need to do. For example, I had a case once where we had a main program that had a couple of different functionalities, different components internally, some modules that did certain things, very different functionalities. And they're all part of the base program if you bought it. But there were some very special functionalities that only very few customers actually needed. And they required some very special care, so we don't include them by default. You would have to request them, and we would give you the DLLs separately if you needed them. That's a precaution. And what we did there was essentially just this. Whenever we compiled the code, we would offload the special code, the special features, into a separate assembly. So we didn't define them in the main program, we defined them in a separate assembly that was compiled with the main program at all times. But when we shipped the basic tool, we only included the DLLs from the main program and left the separate special versions out on the side, and then just gave them to the customer when they needed it. But that means for every version of the main program we compiled, we always had one exact match and DLLs for all the special feature versions, special DLLs. And so we didn't have any issues with compatibility. It was always exactly the right DLL. It was compiled for that exact main program. If you have a game or something like that where you want people to create their own plugins that are supposed to work for a long time, well, once you make an update, things can get difficult. This involves now version numbers. When you compile your assembly, it will probably have a version. Let's actually add that here. With SDK version, let's say this is 1.0.0, first version of the game. Let's say this also gets a version 1.0.0. This is the first version of the plugin and the first version of our main game. Let's just compile the plugin runner. Everything works. Let's try the main program. Plugin's running. That works. Nice. Now let's say we make some changes here. Default is, let's change the typo in here. We recompile, but actually let's update the version. This is now 1.0.1 and recompile. Let's try the code again. Plugin is running. Cool, that worked. Let's change this because I want to have string message. Yep. String message. I want to be able to add a message to my output here. From main. So. And I want to use this code. I make an update. This is now version 1.1.0. Oh. Well, this is an issue. You can see the... Yeah, I can see the exception. I was worried you can't see that, but... We cannot find a match for the run method. Why? We implement iRunner in the interface, but we implement iRunner from an older version of our project. So this iRunner has a breaking change in it. The external library expected a run method without any arguments, because that's what it was compiled for. But sorry, the sneeze is coming up. Okay, no, suppressed. It's suppressed. Ooh, okay. When we compiled this external library, it was for an older version of our main program, so it doesn't have the argument. So the new version for main program is now looking, of course, for the new version of the plugin, which doesn't exist. We would first have to recompile this tool for the new version and then publish that. Effectively, your game had an update and now all your mods need to be updated too before they are compatible again. And that sucks. So if you want to be aware of that, you can't just make breaking changes like this. We can't just add arguments to my run method. But I still want that feature. So what do? Well, simplest case, we leave the old interface method there and add a separate method, one that accepts a message. We can even mark the old one as obsolete if we want. Use run string. Yeah, let's keep it like that. And we do it like that. In our own default code, we can of course simply do this and then call the default run with an empty method maybe, or with an empty data package. And that way, the old code still works. That creates a new issue. If I compile this and run it, we still have an issue with the run method. Because, sure, we do fulfill the condition for the run method that we called before, but now it's missing another method. And that is an issue in old .NET versions. But since we're working with .NET 9 right now, the newest C# language, we can do something cool. We can add default implementation for this method. Did you see what happened? Let's try again. This is the console output. This is all there is. Can you guess what happened? Spoiled it. We loaded the external types and we found the plugin runner. Now, plugin runner, as you can see right now, doesn't have an error anymore because it's missing one of its two methods. It's missing the run overload with an argument. But because we have a new language feature here, the run method with a message argument is no longer mandatory. Interfaces can have default implementations, which is a bit like if you imagine an abstract class. This would be an abstract method. You just define the signature and that's it. And this would be a virtual method, one that you expect to be overloaded, but that doesn't have to be. So this is the code that's used if you do not provide code yourself. I can actually drop it in here as well. Well, okay, sort of. I'm calling the run method, but let's just demonstrate again. Let's make this empty. So there's no call anymore. So this is better. I'm implementing iRunner and I'm only adding the run method, and the run method with argument is just using the default implementation from the interface. So that's a newer feature. I'm not sure when it was added exactly, but default implementations and interfaces are a thing now, and that makes things like these plugins a lot easier, because to avoid backwards breaking, I can add new methods and add them with a default implementation, so the old plugins that don't have them will automatically get an implementation for them without recompiling the old code. Of course, my default implementation isn't doing anything, so interface default is running. Yeah, let's call it like that. And now I can instead update my code. In my external library, I do have now the option. I don't have to do that to make the code work. My library would still be loadable in the game. But now I can make the actual update, and let's call it public void run, like that. I now have to actually make the implementation for run, because that one is not optional. And I compile it. Now run the main program again, and plugin is running. So that's the works. And if I drop this all together, and compile and run, then the default is running. Not the interface default, just the default. That's how with newer versions you can make small changes while still avoiding backwards breaking changes. But at some point you just want to drop the run method altogether. Like, this is already good standard. You are still compatible with older versions of the external libraries of your plugins. but you also offer them the new functionality. So if someone recompiles their old code for your new version of the main program, it all works. But now you want to make a change that absolutely cannot be made backwards compatible anymore in here. You actually want to completely drop the name run, or maybe you want to reuse the run name for something completely different. In any case, just adding a new method in here doesn't work for some reason. Your solution then is to make an entirely new interface. So right now we have iRunner. We can just make an iRunner2. So usually you would change the namespace, not just the class name, you would change to a newer namespace. You change your API from version 1 to version 2. And the important part is that, just like before with the run method, we are keeping the old interface still around. We're gonna make this all obsolete. Use runner2. So old plugins can still refer to iRunner, and we would understand that. But our version 2 just has a new method. And let's execute like so maybe. Again, ideally you would put that in a different namespace, not rename the class name, but in the end that's more or less the same. And you change your code a bit. So in here, I tested for iRunner. What's a non-check for iRunner interface 2 type? Let's call it that. And then type. Let's rename this interface 1 type, interface 2 type, implementing 1 type. I'm going to be a bit lazy with the names. Any equals the interface 1. Oh, I forgot the break before. Okay, my bad. No pun intended. Let's double it, and then we're gonna do interface 2 type. So, simple explanation of what we did. We're going through all the different types again, and we're checking, just like before, if there is an implementation of our runner interface in this type. Actually, let's make this a bit more efficient, just in case. Yeah, that makes a bit more sense. We could also simplify this down to one single loop to go over everything. Okay, let's not go too crazy right now. I don't really care anymore. We're checking if interface 1 is implemented, in which case we store that as the type for that's what we have, or we check for 2. And then we can make this code if implementing 1 type is not null. We do this, we already know this is not null. I'll do this code, and we double this up if implementing 2 type is not null. Default runner 1, and let's make another class, public class default runner 2, and this will implement the execute whatever it does. Executing default like that, and that means we have to call execute. All right. With this, we can now read two different interfaces or two different versions of the interface from our external library. Actually, we should probably make this an else, not just an if. We're checking for interface version 1, and if we can't find one, we try interface version 2. And if we find version 1, we use our old code for version 1, and if we find version 2, we use the new code for version 2. So run this code. Plugin is running from main to main. So our old code is triggering. If we recompile this to version 2, execute, return 1, recompile. We do nothing because the new execute method doesn't actually show something. That's actually at the output, forgot that. Plugin is executing, recompile, and run. Okay, that's better. So, depending on what the external library now has, we assume a different library interface version and run different code. This way, old interfaces or old libraries using the old interface are still usable, but we can also use the new interface. And this way we are still backwards compatible. We can still run the old mods, so to speak, if this was a game. But this code is now a bit more complex. And now imagine I don't have just one single method, but a whole bunch of them. And maybe many, many different interfaces for different purposes. I somehow have to keep track of which interface to use and how to call these different methods and how I can do what I want to do in different circumstances. Like right now, these are more or less the same in purpose, but this one receives a message value, this one doesn't. This one returns a value though, this one doesn't. So depending on which version of the interface I'm calling for backwards compatibility, I have to do slightly different things. And to make your life a bit easier, we don't call these directly anymore. We package this code into its own class that keeps track of everything and that does the necessary translations for us. We're going to create a new class. I'm going to call it adapter, because it will work as sort of adapter. And adapter will either receive public adapter by runner, and store that. Or we're gonna receive by runner 2. Like that. And we're gonna add one method, public void, public int. This adapter is now gonna use the newest standard we have, which is returning an integer value, and call runner. Let's give it some neutral name. And it doesn't provide a string value. But internally, we can, if runner is not null, then we call runner and provide just a default empty string. And it's complaining why. Oh, right, it's not. Yeah, my bad. Like that. And return a default value, 0, for example. If runner, actually at this point we should assume runner 2 is there. Runner 2 dot execute dot return. All right. We can now get an adapter, which, if that is the case, then adapter equals new adapter with an instance. Or we'll get that instance. And down here, we just have to call runner. Oh. Let's throw new exception. No interface found. Let's actually no. Let's call adapter equals new adapter and then new default runner 2. That makes more sense. Right, took a bit longer, but this logic, just depending on what we find, initiates a new instance of the proper runner method in either the old interface version or the new one. And with the old interface version, it could be the oldest compatible version, which only knows the run method, or it could be a new one that also knows the run method with an argument. Both cases would work because we have a default implementation. And we put that in a simple class adapter, which then will translate our call to whatever interface it actually uses. It's a very primitive way to do that, very simple-minded, but it does its job. So I can hide all of this. I don't care about that. In the end, I just have my adapter, and no matter which version of my external library I'm loading, it will call that. If necessary, with default values. And let me just quickly copy something out. For later on, and bam. All right. So our plugin works by having an interface in the main program that gets plugged into, that the libraries, the plugin libraries, know and can use as a common ground when communicating with the main program. The main program will then just check the different files we have to load the assembly, the necessary assembly files, look for any type that implements that interface, our common ground. And it is actually built to accept different types right now. So we are backwards compatible, accepts older versions of the library and newer ones. And then when it found them, it will all put them into one single adapter that will translate your call from your actual main program into whatever the underlying system will be in the end. If we didn't have any libraries, it will just use a default implementation that you provided yourself. And if it did find any interface, it will try to translate this call into the closest match using that specific version of the interface. So it's designed after the newest interface version, iRunner 2, which doesn't expect an argument and returns an integer value. So that's what we're going to do here. If it's using an older version of the interface, the iRunner one, it will call run, or well, run with an argument and return simply a default value. So plugin directly is the easiest way, works directly, has the problem with compatibility. By adding a few steps like be careful about signature changes, just add new methods with default implementations instead of replacing them, and allow for newer interface versions to be loaded as well. And then match everything together into one single class for convenience. With that, you can get a pretty reliable plugin system that can work across a large range of versions. This is not the ideal, of course. There are more complex ways to set up plugins. that are also more compatible, because this one relies on basic .NET calls, of course. So what we do in here is we load an assembly and handle the files directly as if they are part of our normal program. That's effectively what we're doing in here. We wrap everything up, but in the end we make the calls as if those files, as if this assembly was part of our main assembly. You can create plugins that do not get loaded as libraries directly. Instead, you have some more complex protocols that help you communicate with those external libraries. Instead of calling code directly, you can send messages over, data packages that get interpreted in a certain way and get data packages back. You can have communications with an entirely different program, basically. And that way you can get a bit more robust code, potentially. But that's a lot more complex and often not what you need. What you should do, however, is isolate your assembly. Let's have a look at the debug output here, because that is actually very useful right now. Let's start the program again and look at the output. You might have ignored this so far, but if you actually read what's happening here, it says here a lot of skip loading symbols, and we don't care about that, it's skip loading symbols. What we care about is this loaded. You can see in the debug output how .NET is loading in new assemblies, new DLL files while it is running, as it's needed. And these are all libraries it will need. It will need the core libraries, it needs of course our library itself that we're running right now. And there's some helper libraries that are also loaded. Part of these system packages. Again, standard libraries that you always have. They're loaded one by one because they're needed directly or indirectly by us. When we step into our code, the main class is called, and we have to load some more classes. And now I'm just stepping over this one line, and let's have a look. This is where we are. This is our last entry, the .NET standard DLL. Stepping over, and now we loaded who needs to DLL. So just as we loaded the other DLLs before, we now loaded this one as well. And we can let this continue to the end. This means that this assembly is now part of our runtime. This assembly is loaded into our main memory. It is now part of this Windows process. And you cannot get rid of it anymore. Once an assembly is loaded, it stays loaded. You cannot unload this assembly anymore. It's not an option in .NET so far. But you can drop an entire chunk of the Windows process. And these chunks, at least what used to be those chunks, is AppDomain. We talked about AppDomain once before for current domain unheld exception. I think we talked about that. Did we talk about that? I think we talked about this at one point, but I'm not too sure anymore. Anyway, AppDomain. AppDomain is basically, if you imagine your entire Windows process, your entire program is one Windows process, and it's composed of several domains, several app domains. And when I say several, it's usually just one app domain, but you can have several of those. And in those app domains, you have, again, assemblies. And those assemblies then have types, and those types have different members, different methods. So it's all just categorizing from one single Windows process to one or more app domains, and each app domain contains assembly, and each assembly contains types, and it trickles all down. And usually you have just one domain, and you can get that through current domain. What we can do is, for example, get assemblies, right? With that, we can check which assemblies are currently loaded in the app domain. Let's do after before, like so. And if we look at the values, before we had 16 libraries. It's the same ones we saw on the debug output, down to this one. And in the after, we suddenly have 17 libraries. Again, the same ones, just this time we have the external library as well. This array, this list of assemblies that are loaded into the current app domain, the right now only app domain, only can expand. It can never be shrunk, because those assemblies might be used in some way. Anything in that assembly might be used in some part of your program, and there is no easy way to get rid of that. So there is simply no function for that. What we can get rid of, however, is app domains in itself. You can just close the Windows process as a whole. That doesn't hurt anyone. I mean, maybe you wanted the program to continue, but we can drop the entire app domain. And with .NET Framework, we had the option to create new app domains. So we had one app domain we start with when we run to the main method. And then in here, you could create additional app domains. And assemblies can be loaded in any of the different app domains. If we just call assembly load file, we load it into the current app domain, which is our single main app domain. If we created a second app domain, a second category of, or second group of assemblies in our main Windows process, we could drop that entire group. The entire app domain could be thrown away, and the first main app domain would still remain and be safe and run. That's how you can unload it. So in .NET Framework, you would not load this plugin directly. You would create a new app domain, and in that second app domain, you would load your plugin files. Or maybe you would even load a different plugin if you have several in different app domains. So one app domain for each plugin, potentially. Depends on how much you want to isolate things. In .NET Core, and subsequently in .NET, we don't have app domains anymore. I mean, we have still some of the basic functionality of the app domain class, but what we have nowadays is AssemblyLoadContext. AssemblyLoadContext. And you can also get the current context to array before. Actually, let's just copy all of this over to after. So just like app domain, assembly load context is actually much more easy to explain. It's a context in which assemblies are loaded. That's all it is. It's just straightforward a group of assembly that are loaded into your program. And you can see them as straight up a replacement for app domain. You load assemblies into an assembly load context, and we have a default one, the main one you start with, but you can also create new assembly load contexts. And this is not quite what I wanted to see. But, well, 16. It's not loading that. Why? Is it not loading that? I'm confused. Did I make some mistake here? Look, I'm not gonna try to figure that out. Assembly load contexts are still a mystery to me for the most part. I'm using them. I've implemented plugin systems myself instead of creating one based on existing frameworks, which is a mistake, I know, but still I did it. And yeah, what you would do nowadays is create a separate custom load context for your plugin, add the assembly in there, and then when you don't need it anymore, when you want to unload the plugin, then you can just drop the entire assembly load context and create a new one with a new assembly in there. And the reason you might want to drop it is, let's Let's see, if I just copy this line over, I still only have the assembly once. I have two different instances here, but I actually have only one instance in my program. This is not entirely clear right now, right? I know. Let's do it this way. So we're gonna run this code, which loads this DLL first. No, that doesn't work because I'm still loading it. Okay, let's make this a bit more complicated. Assembly dot. Yeah, let's do it like that, and then read all bytes. Okay, that should work now. So we load the assembly. This time I didn't load it from the file. Instead, I read the file into a byte array and fed that byte array into the assembly.load method. It's not quite the same process, but the end effect for us is the same. We load that assembly into our program. So we have read it. Now let's go in here and plugs and executing, hooray, and recompile this. And actually, Solution Explorer, let's rename this. This is version 101. We compile. Nope. Can I not compile while it's... Because the main program is... right. Okay, too bad. I can't quite demonstrate it now. I would have to make copies of the program and I'm too lazy for that. Well, the issue is the assembly can only exist once. We can't just have different versions of the assembly running around in the same context we have right now. So let's say I have a plugin that I load, and then I want to change the plugin because maybe I want to make an update of it. I want to download a new file and replace the existing one. If I don't have an AppDomain or an AssemblyLoadContext I can drop it with, the assembly stays, the old version of the assembly stays loaded in my main program. I won't be able to replace it with a new one because that assembly has a unique name and that can only be in your program once. You can have only one version of that assembly in your program. By having different app domains or AssemblyLoadContext, you can have the same assembly many times, as long as you spread them into different domains or load contexts. So one reason why you want to spread them out is to have more versions of the same assembly, but often it's also just so you have the ability to unload it if necessary. Or for example, you notice something is wrong with the file and for security reasons you want to drop it. You can drop the app domain or AssemblyLoadContext. Get rid of the plugin that way. Again, those are more advanced systems. There are actual frameworks, even from Microsoft directly. They have plugin frameworks that you could look into that are rather mature, and if you use those successfully, then you're good to go, I guess. You can also try to make your own system. If it's really very straightforward, simple idea of, hey, when I start my program, I want to include these other libraries, maybe as a modification to my main program, as a legit mod, or just plugins. Well, just load the file, just check all the files in a subfolder you have, read all those DLLs, and for each one, try to find the interface you've defined. And just make sure that people who create plugins for you have access to that one DLL. So for example, I could put my interfaces into a third project in here. And the main program depends on that third project. And the third project itself doesn't have any dependencies, and you could give that DLL out to your plugin developers. So you could give out a DLL that contains nothing but these interfaces. and both your main program and those external libraries both depend on that DLL, on that interface containing assembly file. That way you don't have to share your main program with developers, and they can still make plugins for you. But yeah, I think that's enough for today. I feel like I didn't quite get across what I wanted to. I was hoping the lesson would go smoother. I shouldn't have dropped my plan. I had the script laid out and I dropped it 10 minutes before the show because I thought that doesn't quite work. I guess improvising doesn't work either. Oh well, we're not going to redo this. Dependency injection and plugins. See you next time.